Climate change and human-caused destruction place many heritage sites at risk. By capturing data for these heritage sites, they can be preserved in a digital form. For representing the captured data, interaction with the physical object offers many benefits in areas of tactile exploration, object manipulation, and circumnavigation. At the same time, however, digital representations can provide visual effects that are difficult to represent physically, such as X-ray views. They may also be better suited for dynamic visualizations and navigating large amounts of associated text and photo media. In our work, we apply augmented reality to 3D printed physicalizations in order to obtain benefits from both approaches at once. In this video, we will first discuss the features of the system we have introduced. Once this context is established, we will discuss some of the technical details behind how this is achieved. We implement our system on two sample physicalization use cases, Old Sun Community College and Pauline Cove. In each case, we can render an overlay that has more visual detail than 3D printing alone allows for. We can also emphasize or display visual details that exist at a smaller scale than the main object. The object of focus, possibly enlarged, is displayed on a separate side platform print and is connected to its location in the main subject via context lines. Interior details can be rendered on top of the exterior with an X-ray view, and walls that would block a view of the interior can be removed. Additionally, these focus items can be rotated around with their platform, so that the user may view different angles without having to walk around the print. Users may zoom and pan in order to view details at a smaller scale than the main subjects. When zoomed in, however, jitter from a user's hand might be more noticeable. In this case, users can take a temporary screenshot that freezes all motion in a scene. When the user is finished interacting with the paused version of the scene, they may exit the screenshot mode and continue using the app as usual. Screenshotting also allows the user to continue interacting with the scene after moving away from the model. Unlike a typical static screenshot, interactive functionality, such as room switching, is still available. Our augmented reality view also allows incorporation of dynamic content, such as satellite images of Pauline Cove over time, without requiring many different versions of the 3D print to be created. Finally, our app has an adjustable side pane that can be used to view text and photographs collected for the heritage sites. Audio files are also included.
I learned how to begin to speak English, but I was following the spoke platforms.
Now that we have covered what the app does, we can discuss the technical details. Researchers commonly use 2D markers to determine an object's pose, but such markers are generally sensitive to changes in lighting conditions, occlusion, and motion blur. Additionally, a marker would have to be in view at all times, which could mean certain views would require the marker to occlude details on the 3D print itself. As an alternative, we used a pose-tracking algorithm that uses the 3D object silhouette. This algorithm was originally written to run on a PC, so we had to adapt it to run on a mobile device. One downside of using silhouettes is that when close to the object, the silhouette can fill up the entire screen and can no longer be used for tracking. We handle this by also tracking smaller objects, such as windows of the school building, that have their own silhouette against the main object, allowing close-up views of the smaller details we render for our subjects. For obtaining an initial pose so that tracking can begin, use of a 2D marker can prove useful, though once tracking has begun, the marker no longer needs to be in view. If tracking is lost, the last view of the object is still rendered, and tracking can resume when it is lined back up with the subject. Additionally, a 2D marker can also be used to resume tracking.